recognize of is that we are not, Gauss's law does not provide for us any sort of new relationship. Because what Gauss's law provides is essentially the same thing that Coulomb's law provides for us, which is the relationship between charge and the electric field. Now, the reason why we teach both is that there are some strengths and weaknesses to both methods. Coulomb's law turns out that not all problems are humanly feasible, whereas Gauss's law makes it, very, very simple. So for Coulomb's law, if you wanted to do the problem correctly, you would definitely need the use of calculus. However, Gauss's law pretty much gets rid of that calculus and turns it into an algebra problem, and we're going to see exactly how that's going to pan out. But before we get to Gauss's law, we have to talk about the ideas that Gauss's law actually uses. And Gauss's law uses this concept called flux. And this flux is simply the idea that something is passing through a certain area. So when we apply the flux to electricity or electric fields, this is what we get. It is simply the electric field dotted with an area. Right? Flux passing through an area, electric flux, electric field through an area. And we ended by doing a simple computation. Now, one thing, and the primary reason why I ended early, is so that here we introduced this concept of a flux as well as a dot product, and I wanted those ideas to kind of simmer while you sleep, Monday and Tuesday, so that when we actually begin to use this, maybe those simmering actually led to a few blossoming of leaves or whatever, throw in some metaphors there. But we're going to talk about how this actually is related, or how this is used to give us a relationship between the charge and the electric field. So this is where we're going to pick up. Now, Gauss's law has some requirements that needs to be met. So we just talked about flux in general, but Gauss's law requires a very specific surface. It requires an enclosed surface. It requires an enclosed surface. So what we mean by an enclosed surface is something that has a definite volume on the inside. So we're going to be working with inherently three-dimensional shapes. Three-dimensional shapes. And let's say there's electric field, comes in, enters, and then leaves again. Comes in, enters, and then leaves again. These are the electric field lines. Now we discussed that the area vector, or the area, has a vector, and that is perpendicular to the surface itself. So actually, let me rewrite the equation so it's on the same page. So phi E is equal to E dot A. Remembering the dot product is simply the product of the two magnitudes times the cosine of the angle in between. Well, what is theta? talk about a convention. So the area vector, we have two options. So at the point of entry, so let's consider this little spot right here. At the point of entry, we have two options for denoting the area vector. We can either point outside or point inside the volume. So which one should we use? Or does it not matter? Technically, it doesn't matter. However, for the purpose of Gauss's law, we wanted to point outward, or points out. So we want to define the vector as pointing out of the volume, so this will be our area vector. Once again, the two options were outside of the volume or into the volume. We want to make sure it points out. Likewise, at the point of exit, here, so we're just considering this portion of the plane, we can draw an area vector, but which direction are we pointing? We have to make sure it points out. So that will be our area vector. From here, we can get our theta. So let me zoom in to the relevant portions here. Our area vector is pointing this away. Whereas the electric field, it's starting from here and it's pointing that away. But at the point of entry, it is pointing roughly in this direction. Would you guys agree? Somewhere along those lines? The theta would be this angle. That would be our angle theta. Let's look at the point of exit. So this would be the entry. So electric field line entering the volume or the closed surface. Here, our area vector is pointing roughly that direction. What about the electric field? It is roughly that direction. And this would be the angle theta, and this would be the exit. So the area vector, we have to make sure it points out because it provides this kind of insight. Notice when something is entering the surface, the angle is very large. Whereas when the electric field is leaving it, the angle in between is very, very small. So when an electric field enters, the angle is very large. And we have a specific range that it will always be greater than pi over 2. What is pi over 2 in degrees? So this is also 90 degrees. So the angle will always be greater than 90 degrees. However, we don't, in terms of computing the flux, we don't just care about theta. What we care about is cosine of theta. What is the cosine of angle that is greater than 90 degrees? You guys remember your unit circles? Cosine of greater than 90 degrees, if you want to plug it into your calculator, will always be a negative number. So cosine will be less than 0. Therefore, your flux will also be less than 0. Because your flux is simply the magnitude of E, the magnitude of your area, times your cosine. E and A are positive values. What determines if the flux is positive or negative simply comes from this angle dependency. So if an electric field line enters, that means you have a negative flux. Whereas if you have an electric field that exits, then you would run into a scenario like this where your angle would be less than, okay, let's just use 90 degrees. Let's not use radians. Your theta will always be less than 90 degrees when the electric field line enters your enclosed surface. And if you can check in your calculators. Once again, we don't just care about the angle theta. What we care about is the cosine of theta. And if you plug in theta less than 90 degrees, you will see that you always get a number that is greater than 0. Meaning that when an electric field line leaves, the electric flux is going to be positive. So what this tells us is it provides deeper insight as to what the flux is actually trying to symbolize for us. The phi gives the flux out of the volume. It is the net flux out of our volume. And that's why when an electric field line is exiting, we say it has a positive flux. So that's why phi greater than 0 tells us net flux is out. Whereas phi less than 0, this tells us net flux is into. So out volume, or out of volume, into volume. All right, let's now cover a little bit about how to draw them. So one of the things that's going to be very important in terms of doing this idea of flux, in terms of visualizing them, is we're going to be using the electric field lines. So they weren't just for drawing pretty pictures, they actually do have some theoretical use. So we're going to be using field lines. And field lines, we're going to be using them because they help represent flux. And to convey that, let's begin by drawing a scenario where you have a positive and a negative charge. So let's draw the field lines. So this is the halfway point. There, something that looks like that. Now, how to apply, or this idea of a flux with Gauss's law? We're going to be using what is called a Gaussian surface. Use Gaussian. Use a Gaussian surface. And what this Gaussian surface is, it is purely theoretical. Purely theoretical geometry. By that, what I mean is, for simplicity, we're going to be using a sphere. This is not a circle, a sphere. A sphere. It's a three-dimensional shape. And we're going to enclose the charges inside of a Gaussian sphere like this. These are examples of a Gaussian sphere. We're not actually placing something like these charges inside of an object. No, that's not what we're doing. This is a purely theoretical thing. We just want to draw a shape around it. It's more of like a mental boundary that we are describing. And here we can make a few different bullet points. First, is that if every line entering also leaves then the flux is going to be equal to 0. And this is the power of the electric field lines. They can actually represent flux, and simply by counting lines, we can come to some understanding of what the flux is. And so if every line entering also leaves our Gaussian sphere, then the flux is going to be equal to 0. Alternatively, the flux is not equal to 0 if and only if either one of these conditions are met. Line ends within the Gaussian surface or line begins within the Gaussian surface. Yeah.
What's the first part of that statement?
Here,
Yeah.
the flux does not equal 0 if and only if. So this IFF is a mathematical term, if and only if. So this is just stating that it's not only the sufficient condition, but the necessary condition, or the only necessary conditions. When will this be true? When will a line end or begin in a Gaussian surface? Well, it's when we have a scenario like this. A line begins at a point charge or ends at a point charge. And so this only occurs if Gaussian surface encloses a charged object. So let's come and analyze this scenario that we have here. Let's label this Gaussian surface A and let's label this Gaussian surface B. And we just want to know from a conceptual visual perspective, is the flux positive or negative or equal to 0? The flux of A, is it positive, negative, or equal to 0? Let's see a show of hands. Who thinks it's positive? Okay, who thinks it's negative? Who thinks it's 0? And who thinks it's none of the above? That's all. It is greater than 0. Remember what flux represents. Flux represents the electric field leaving the surface. And here we have a positive charge, and all the electric field lines are pointing which direction? Out or in? All of the field lines are pointing out, so we have a net outward flux of the electric field, so it's going to be equal to 0. Or we could do this more mathematically. We can actually look at the angle in between the electric field as well as the area. At this point, the area vector would be in which direction? Remember, we have to stick with convention. The area vector must be pointing out. And the area vector must be perpendicular to the surface, so that would be our area. What is the angle between these two? Greater than 90 or less than 90? Right, so less than 90, plug it into your calculators, you're going to see that cosine of less than 90 is positive. Therefore, you're going to have a positive flux. Whereas over here, we need to be consistent with how we draw our area vectors. Once again, they have to be pointing out. That will be our area vector. And this time, our area vector is up, whereas the electric field vector is down. What's the angle in between? Greater than 90 or less than 90? Right, it's greater because it's roughly 180, right? It's roughly 180. And if you plug in cosine of 180, you're going to see that it's a negative number. And so here, the flux of B is less than 0. And you could do this with theta. Theta is going to be less than 90, meaning cosine of theta is greater than 0. So here theta is greater than 90 degrees, which means cosine of theta is less than 0. Yeah?
Wait, so A is positive and B is negative, or other way around?
A is positive and B is negative. But when would you get a scenario of this kind? When would you get a scenario of that? Yeah, 0.
Can you, could you do that if you draw the Gaussian spheres bigger to include both of the charges?
Yeah, yes, you can choose whatever Gaussian sphere you want. If you choose that one, you can see that this one leaving also enters, right? Leaving enters, vice versa. Alternatively, you could just draw a Gaussian surface right here. This one enters, but it also leaves. And so those are the different scenarios. And so what I was hoping to convince you of by this set of examples is to notice that the flux depends on the charge enclosed. It depends on the charge enclosed. Here, on our surface A, the Gaussian surface enclosed a positive charge, therefore there was a positive flux. B enclosed a negative charge. So there was a negative flux. And like I was saying, if you just enclose nothing, your flux is 0. And so the charge enclosed does determine what your flux is going to be. So this is a qualitative observation. But of course, this is a college level class. We don't just care about the qualitative, we care also about the quantitative. We want to know what is the quantitative relationship between them. What is the quantitative relationship for this? And the answer to this is what is called Gauss's law. So we have finally talked about all the different ideas that lead to Gauss's law, so we can now begin talking about what Gauss's law actually is. So let's talk about Gauss's law. Gauss's law provides for us that relationship that we desire from the flux to the charge that's enclosed. Gauss's law tells us this, that the electric flux which remember is equal to E dot A. Gauss's law tells us that this entire thing is equal to the charge that's enclosed divided by epsilon naught. And yes, this is that same epsilon naught that is related to the Coulomb's law constant. It is equal to 8.85 times 10 to the negative 12 Coulomb squared Newton meter squared. And so this is where that epsilon naught idea really comes from. It comes from Gauss's law. So notice what happens. We have a relationship between the electric field and the charge. That's what Coulomb's law provided for us, right? Electric field to the charge. So like Coulomb's law, Gauss's law relates E to Q. So let's compare. And let's compare and see what information Coulomb's law gives us versus what information Gauss's law gives us. Coulomb's law tells us that for a point charge, actually we're going to analyze the point charge for now. And Coulomb's law tells us that essentially the electric field is equal to KQ over R squared. You guys remember that? You guys remember that? So this you can get from experimental verification. But let's see what Gauss's law provides for us. So we have the point charge, and we can draw the electric field lines to guide our thinking. Because it's a positive charge, it's radiating out. Now I'm going to tell you which the Gaussian surface to be used here. But I'm going to give you more details on which one to use in the future. We're going to be using a sphere. So we want to use the Gaussian sphere. Gaussian sphere. With this in mind, all we're going to be doing, let's say with radius r, with radius capital. With this sphere, remember it's purely theoretical. We're not putting this charge in any sort of a sphere or anything. It's a mental sphere that we are utilizing. And we are going to apply Gauss's law to this enclosed surface. And so what are we going to get? We're going to get E dot A is equal to Q enclosed over epsilon naught. Let's just focus on the left-hand side here. What is E dot A? The reason why we wanted to use a Gaussian sphere is because we get this relationship EA times cosine of theta. What is theta? We use a sphere because regardless of where you are on the sphere, you have the same theta. And what is that theta? So all of your areas are going to be this, and at this point, the area is going to be that. What is the angle between your area vector and your electric field vector? What's the angle between? Is it greater than 90?
Yes.
Really? How's it greater than 90? So here, our area vector is here, and our electric field vector is there. For that. What's the angle on this one?
Zero.
Yeah, the angle's 0. What about here?
How is that different from another region that was kind of on top of it also?
The one? Where?
Is the charge coming inside?
Yeah, because the charge was coming inside.
Oh.
Electric field was going inside. But we're focusing on electric field going outside. But you can see at every single point, the electric field going out and the area going out is constantly the same, and it is going to be the theta is what? 0 degrees. Who remembers what cosine of 0 is? Cosine of 0 is 1, and this simply turns into the electric field times the A. This is the surface area. Who remembers what the surface area of a sphere is? Nobody knows? Yeah.
I just actually want to just a super quick question. Is E dot A meaning something different than E times A?
Yes, it's the dot product, and we discussed this on Monday.
Okay, just
So A dot B, this is a definition of a dot product, is AB cosine of B. That's what the dot product represents.
okay.
It's the product of the magnitudes times the cosine of the angle in between.
Okay.
So that's why we have this. And so that's why I was asking about what is angle theta between the area and the heat.
I was just double checking.
So the surface area of a sphere, this is something that you might want to write down, is 4 pi r squared. meaning this entire left-hand side is 4 pi r squared times E. Now let's equate that to the right-hand side. Okay. So we have 4 pi r squared, 4 pi r squared E is going to be Q enclosed over epsilon naught. And if we isolate for E, what are we going to get? This is going to equal 1 over 4 pi r squared, so 4 pi epsilon naught times Q enclosed over r squared. What is 1 over 4 pi epsilon naught? This is also K. So this is also equal to K enclosed over r squared. Where have we seen this before? Apparently nowhere.
Cool.
All right, this is exactly Coulomb's law. In Coulomb's law, this expression was kind of a starting point. You could say it was derived from experimental results. Yes, that's fine. However, Gauss's law provides us leads us to a fundamental understanding of why Coulomb's law is the way that it is. So Gauss's law, once used properly, will lead to the same information as Gauss's law. Gauss's law, as long as you do it properly, will lead you to the same information as Coulomb's law. Now with that, let me write a few helpful tips and observational notes. One is choose, the key to you using Gauss's law, I'll say correctly, comes in the idea of reducing this down into simply E times A. So it's method of trying to get rid of the angle dependency. So that's why we chose a Gaussian sphere. So the first tip, or the key to doing Gauss's law correctly, is to choose Gaussian surface such that theta is going to equal 0. So the Gaussian surface can be whatever you want. So choose the one that's most convenient, and that's the most convenient is one that gives you a angle dependence or the angle difference of 0 degrees. Also, Coulomb's law simply tells us that the flux is equal to Q enclosed. It has zero concern for how that charge is distributed. Okay? So the distribution of the charge inside doesn't matter. It doesn't matter if it's all collected onto a single point or evenly dispersed. It doesn't matter. So the charge distribution inside does not matter. Only the magnitude does. Yeah. So is it all focused on a single point, or is it evenly spaced out? So you only care about Q enclosed. Oh yeah, sorry. You only care about Q enclosed. There's nothing about how the charges are spaced out. So if you have 5 electrons, and let's say one scenario, you have this or you have that, they have the same charge as long as you enclose them on, these both have the same Q enclosed.
Oh, I
But you
see.
can see that these are spaced further away than this one, but
Okay.
it doesn't matter.
Okay, that
Yeah.
makes sense. Thank you.
Also, the charge outside does not matter. Contributes 0 to phi. Alright, so these are some observational notes. So you can see that point charges for Gauss's law and Coulomb's law, they're the same. And we get to the same relationship. For the calc-based class, we derived the electric field from a wire using Coulomb's law, and that's when you guys got the benefit of not coming to class. And that single example took, I think, roughly 1 hour. Okay. We're gonna do that using Gauss's law in like 30 seconds. So that's one of the benefits of Gauss's law. Coulomb's law, technically you can do it, but it takes a really, really long time. One of the benefits of Gauss's law is instead of having calculus, it turns into a very simple algebra problem, and let's see how that works. So applying Gauss's law. So essentially, the question that we want to answer is what is the electric field of a infinite wire? So the scenario that we are considering is this. I forgot to mention something. Okay. So we want to choose a Gaussian surface such that the angle is equal to 0. And often you want to use sphere or cylinder. These are two common geometries that you want to be using. I forgot to mention that. And so let's say we want to consider a point where we are, let's say, well, not x, r distance away from the center of the wire. Well, what is the electric field at this point? Now, we're not going to go over Coulomb's law methodology together, but I am going to write for you the different steps that were required so that you can get a sense of how much easier life becomes. So using Coulomb's law, we would first consider a finite, not an infinite, so we are looking at a different object. Consider a finite rod. Finite rod. A finite rod is not a point charge. Coulomb's law is only applicable to point charges. But this infinite wire, there's no reason why we can't, at least mentally, slice this up into very small pieces. Right, we can do that, right? At least consider it. You're not actually cutting it up, but let's just say, instead of thinking of this as one large piece, let's think of this as many small pieces stacked on top of each other, right? It's okay to do that. Now these now look like point charges. Does that make sense? So you divide rod into small, approximately point charges. And why do we do that? Because now that we have roughly point charges, we can apply Coulomb's law. So here, apply Coulomb's law to each point charge. And do you remember that example with 3 point charges, and I asked you to get the electric field on the x-axis? We did that in class, and that one took like 45 minutes. That was only 3 particles. Imagine doing it for many, many, many more. That's what Coulomb's law becomes. So we apply Coulomb's law to each point particle, 3, then we can get the net electric field by summing up all of the electric fields from the point charges. And we're still not done, because this is the electric field of a finite rod. So instead, this would be the electric field of a rod. But to get to an infinite wire, you would have to take the limit as the length approaches infinity of the rod, and then you would be able to get that this is the electric field of an infinite wire. And it is these steps that may it take like pretty much an hour to actually do. And I did give you the solution that this was equal to 2k lambda over r. 2k lambda over r. Well, now let's use Gauss's law. Let's redraw our scenario. We have an infinite wire. And we want to know what the electric field is at a point r distance away. So the only thing that we have to do is be cognizant of which Gaussian surface we want to choose. And remember, we want to choose it so that the angle is going to be equal to 0. So in a wire problem, which geometry would you like to use?
Cylinder.
Cylinder. Why did you choose a cylinder?
A wire is a cylinder.
Yeah, because a wire is, a cylinder, and that is correct. We want to use a cylinder with the radius of r. The cylinder that we're going to be using